global transition to green steel is hitting a physical barrier. While capital flows toward building electric arc furnaces, the critical bottleneck lies upstream in mineral processing. Direct reduced iron systems operate in a solid state and require ultrapure iron ore pellets. Standard blast furnaces can absorb high impurities, but direct reduction requires an iron content of 67% or higher. The data plots a severe structural divergence. By 2030, global demand for direct reduction-grade pellets will reach 220 million metric tons. Operational supply is projected to flatline at 140 million metric tons. This leaves an 80 million ton deficit that threatens to stall over a third of planned green steel capacity. This supply deficit is driving a steep economic penalty. The price premium for high-purity pellets over standard iron ore fines has doubled since 2020, reaching $55 per ton. This premium is dictated by the strict thermodynamics of steelmaking. If combined silica and alumina impurities exceed 2%, the operational economics collapse. Every single percent of excess silica adds 30 kilowatt-hours of electricity consumption per ton of steel. It also increases electrode wear by 0.5 kilograms per ton. In an industry operating on thin margins, these physical penalties make lower-grade ores economically unusable in electric furnaces. The green transition cannot bypass these basic chemical constraints. Supply of this critical raw material is highly consolidated. 3 Western-aligned producers control 72% of global merchant capacity. This concentration introduces severe geopolitical and geographic vulnerabilities. Sanctions have largely isolated Russia's 10% market share from European buyers, forcing a scramble for Swedish and Canadian supply. This bottleneck mirrors the late 19th century transition to the open hearth process. At that time, the chemical limits of early Bessemer converters forced a geopolitical scramble for low-phosphorus Swedish magnetite. Today, the green steel transition is similarly tethered to a handful of highly specialized mines. Any infrastructure or climate disruption in Brazil or northern Sweden will immediately halt global decarbonization timelines. Superconducting quantum computing is scaling toward a hard physical limit. Qubits require operating temperatures near absolute zero, which is only achievable using dilution refrigerators powered by Helium-3. This isotope is exceptionally rare, sourced almost entirely from the radioactive decay of tritium in nuclear weapons stockpiles. The supply chain is structurally decoupled from commercial market forces. The data reveals an imminent supply collision. Global Helium-3 production is contracting as legacy nuclear stockpiles decline. Simultaneously, quantum hardware demand is expanding at a compound annual growth rate of over 30%. By 2026, quantum demand alone will exceed total global annual production, forcing a rapid depletion of finite national reserves. This structural deficit is already generating severe economic friction for hardware developers. Since 2018, the spot price of Helium-3 has surged by more than 300%, reaching $2,750 per liter. This bidding war is accompanied by severe manufacturing backlogs. Lead times for high-capacity dilution refrigerators have tripled to 18 months. The capital expenditure profile of quantum research is shifting rapidly. A standard 40-liter gas charge now costs $110,000. This single gas input represents up to 25% of total refrigerator system costs. Startups and research labs face prolonged delays and escalating capital requirements before they can cool a single processor. The physical bottleneck worsens as qubit architectures scale. While academic systems require only 12 liters of Helium-3, next-generation fault-tolerant systems require 150 liters per unit. The 8 fault-tolerant prototypes planned or active today lock up over 1,200 liters of gas. This represents more than 11% of entire global annual production. This isotopic bottleneck is structurally analogous to the early 20th century radium squeeze. Pioneering nuclear and medical research was throttled for decades by the extreme scarcity of radium, controlled by a Belgian monopoly in the Congo. Today, the frontier of advanced computing remains tethered to a scarce nuclear byproduct. Without alternative cryogenic technologies or new isotope extraction methods, the quantum roadmap will remain physically constrained. Global electrical grid modernization is colliding with a critical chemical bottleneck. Regulators are forcing a rapid phase-out of sulfur hexafluoride, the most potent greenhouse gas known. The primary replacement for high-voltage applications is fluoronitrile, known as C4FN. However, the supply chain for this eco-gas is facing an immediate capacity cliff. The data illustrates a severe structural divergence. By 2030, global demand for C4FN will reach 4,000 metric tons. Yet, the primary global producer, 3M, is exiting all fluorochemical manufacturing by the end of 2025. This exit drops global capacity to just 400 metric tons in 2026, triggering a 900-ton deficit. Commissioning lags for new high-pressure reactors mean this deficit will persist through the decade. This chemical deficit is translating directly into grid infrastructure delays. Lead times for SF6-free high-voltage switchgear have doubled since 2020, reaching 120 weeks. At the same time, the capital cost premium for these units has surged to 45%. Utilities face a dual penalty of extended project timelines and escalating budgets. These cost increases are driven by fundamental physical differences between the gases. C4FN has lower low-temperature performance than sulfur hexafluoride. To compensate, equipment manufacturers must design larger, high-pressure multi-chamber enclosures. This increases the volume of specialized aluminum and steel required per unit. The physical reality of chemical substitution is inflating the cost of grid decarbonization. The transition presents a stark trade-off between environmental performance and supply chain security. C4FN mixtures reduce global warming potential by 98.5% while retaining 95% of the insulating strength of SF6. This makes it the only viable chemical for high-voltage transmission. However, its supply chain concentration index stands at an extreme 85 out of 100. Alternative technologies, like dry air, eliminate supply chain risk, but carry a severe physical penalty. Dry air has less than half the insulating strength of SF6. Using it requires massive equipment footprints, which is impossible in space-constrained urban substations. This structural lock-in to a highly concentrated chemical supply chain mirrors the mid-20th century phase-out of polychlorinated biphenyls in transformers. When those toxic coolants were banned, utilities faced a decade-long scramble to redesign grids, proving that chemical transitions always dictate the pace of physical infrastructure. The global steel supply chain relies on a single, highly vulnerable marine corridor. Western Australia's Pilbara region produces over half of seaborne iron ore imports to China. This entire volume must pass through the port of Hedland's narrow 42-kilometer shipping channel. As export volumes have risen, the physical limits of this channel have become a critical operational bottleneck. The data shows a direct correlation between throughput and maintenance dredging. Annual iron ore exports reached an estimated 573 million metric tons in 2024. To maintain the required 18.5-meter draft, annual dredging volumes scaled to 1.8 million cubic meters. Fully laden Capesize vessels are now restricted to a strict 2 to 3 hour high tide window. This operational envelope leaves zero margin for mechanical or logistical errors. The lack of redundancy at the port-rail interface creates an extreme single point of failure. A single day of channel closure or rail-to-port car dumper failure halts 1.5 million metric tons of exports. This single-day disruption inflicts a direct revenue loss of $150 million. The financial shockwaves cascade immediately into global spot market pricing. The physical mechanics of the port compound these delays. Because Capesize vessels must depart in a precise sequence, a 12-hour delay pushes multiple ships out of their tidal windows. This triggers immediate demurrage penalties and disrupts downstream blast furnace schedules in Asia. This vulnerability is structurally identical to the late 19th century Great Lakes bottlenecks. The entire American steel industry then depended on the dredging depths of the St. Mary's River and the Sioux Locks. Today, global steel production remains similarly tethered to a single dredge channel. This logistical risk is highly consolidated among a few corporate actors. BHP and Fortescue jointly control over 84.8% of the tonnage transiting the port. Roy Hill's expansion to 63 million metric tons has further congested the shared marine infrastructure. The physical reality of the Pilbara corridor is a shared risk model. 3 mining giants rely on the same 42-kilometer channel to reach their primary market. Any localized physical disruption immediately threatens over half of China's steel-making raw materials. While companies invest billions in autonomous rail and pit-to-port automation, they cannot bypass the physical limits of the harbor. The pace of global industrial production remains governed by the depth of a single shipping channel. Industrial scaling of synthetic sapphire is governed by extreme thermodynamics. The Chiropoulos crystallization process requires melting high-purity alumina at temperatures exceeding 2050 degrees Celsius. Maintaining this thermal state requires weeks of uninterrupted electrical baseload. Any power fluctuation lasting only milliseconds causes thermal shock, instantly cracking the crystal. The data reveals a compounding penalty when scaling ingot mass. Increasing ingot size from 85 to 120 kilograms extends the growth cycle to 22 days. This longer run consumes nearly 42 megawatt-hours of electricity. It also accelerates the volatilization of the iridium crucible, driving wear costs up by 56%. This degradation compromises the economics of larger runs. As ingot mass increases, average yield rates drop from 65% to 55%. The risk of microcracking during the cooling phase rises with volume. Producers face a structural trade-off between throughput and catastrophic batch failure. The physical bottleneck in crystallization is compounded by an upstream raw material deficit. Synthetic sapphire manufacturing consumes over 65% of global 5N high-purity alumina. This ultrapure input is highly concentrated in specialized refining facilities in Japan and China. The data shows demand outpaced supply starting in 2023, creating a structural deficit. This deficit is driving a rapid escalation in material costs. The price of 5N alumina is projected to rise by 116% between 2020 and 2026. Producers cannot substitute lower-grade alumina to mitigate costs. Impurities exceeding just 1 part per million cause optical absorption bands, ruining the crystal for high-power laser and semiconductor applications. This structural vulnerability mirrors the synthetic quartz crisis of World War II. In the early 1940s, the Allied war effort was bottlenecked by its reliance on natural quartz imported from Brazil. The threat of maritime blockades forced a crash program to develop synthetic hydrothermal quartz. Today, the semiconductor and optoelectronics industries face a similar structural constraint. The frontier of advanced optics remains tethered to a highly concentrated chemical refining bottleneck. Production of advanced fluoropolymers is bottlenecked by a highly concentrated chemical precursor. Anhydrous hydrogen fluoride is the foundational input for lithium-ion battery binders and semiconductor etching. Yet, the physical capacity to manufacture this hazardous chemical is almost entirely centralized. The data shows a stark geographic imbalance. China's share of global production capacity expanded to 74.5% in 2024. Meanwhile, North American and European capacities remained virtually stagnant. Combined Western capacity grew at a compound annual rate of just 0.54%. This stagnation is driven by regulatory and capital barriers. Strict environmental compliance costs on fluorine emissions discourage greenfield investments in Western jurisdictions. This regulatory asymmetry cements a deep systemic dependency on Chinese chemical parks. The global supply chain is structurally exposed to this single point of failure. This geographic concentration is colliding with the rapid expansion of global gigafactories. Lithium-ion batteries with high-nickel cathodes require polyvinylidene fluoride, or PVDF, as a binder. Synthesizing battery-grade PVDF requires ultrapure anhydrous hydrogen fluoride. The supply-demand balance is diverging rapidly. Global demand for battery-grade PVDF is projected to reach 350 kilotons by 2030. This represents a compound annual growth rate of 22.7%. The structural deficit in purified AHF capacity allocated for this material will reach 90 kilotons by 2030. The bottleneck is physical, governed by highly specialized metallurgy. Purifying AHF to the parts per billion threshold requires reactors lined with specialized nickel alloys like Hastelloy. Lead times for these corrosion-resistant chemical reactors now exceed 18 months. Downstream battery manufacturing cannot scale faster than the specialized chemical equipment can be built. Economic friction of this bottleneck is concentrated entirely in the purification step. Raw fluorspar mining is not the primary constraint. Instead, the value add and the pricing pressure occur during chemical distillation. The pricing data confirms this structural divergence. The price of ultra-high purity hydrogen fluoride surged to $10,200 per metric ton in 2024. This represents a 142.8% increase from 2019. In contrast, industrial-grade AHF rose only 50% over the same period. Purification is an energy-intensive, multi-stage process. Removing trace arsenic and boron impurities accounts for 42% of the total production cost. This chemical dependency mirrors the early 20th century reliance on German synthetic organic intermediates. Before World War I, Western industries were entirely dependent on German coal tar intermediates. Today, the global transition to advanced semiconductors and electric vehicles remains tethered to a highly concentrated chemical purification bottleneck. The Port of Montreal is operating at its absolute physical limit. Legacy urban terminals are capped at a structural capacity of 1.70 million TEUs. This ceiling triggers severe yard congestion and spikes container dwell times during peak import seasons. Without expansion, the St. Lawrence Logistics Corridor faces a structural deficit of 280,000 TEUs by 2030. This capacity shortfall will force cargo diversion to deepwater United States East Coast ports. The Contrecoeur terminal expansion is designed to resolve this bottleneck. Located 40 kilometers downstream, it adds 1.15 million TEUs of annual capacity. This represents a 67.6% expansion of Montreal's total throughput potential. The bottleneck is fundamentally geological and structural. The St. Lawrence River Ship Channel restricts Montreal's legacy terminals to an 11.3-meter draft. This shallow draft caps vessel sizes at approximately 5,000 TEUs. Furthermore, the Jacques Cartier Bridge imposes a strict 49-meter air draft restriction. Contrecoeur bypasses these upstream physical barriers. Its downstream location increases draft clearance to 12.5 meters. This allows access for vessels up to 8,500 TEUs. Yet, Montreal still faces a structural scale disadvantage against deepwater coastal competitors. Halifax offers a 16.0-meter draft. New York and New Jersey provide 15.2 meters. These ports easily accommodate ultra-large container vessels exceeding 16,000 TEUs. Contrecoeur is a defensive necessity to prevent Montreal from becoming entirely obsolete. Scaling physical infrastructure requires navigating extreme regulatory and financial friction. Projected capital expenditure for Contrecoeur has escalated by 86.7%. Estimated costs rose from $750 million Canadian dollars in 2016 to $1.4 billion Canadian dollars in 2024. A primary driver of this delay was environmental mitigation for the endangered copper red horsefish. Protecting this single species forced extensive design modifications and delayed the project by 3 years. A transition to a design-build-finance-maintain model in 2023 pushed the final opening to 2029. This downstream migration of port infrastructure mirrors the historical evolution of the Port of London. As vessel drafts grew, London's historic urban docks became obsolete, forcing a migration to Tilbury and London Gateway. Montreal is repeating this structural pattern, proving that logistics networks must ultimately adapt to physical geography. The transition to high-energy density electric vehicle batteries is hitting a chemical processing wall. While capital focuses on raw mining extraction, the true bottleneck is upstream crystallization. High-nickel cathodes require battery-grade nickel sulfate purified to single-digit parts per million. Without this ultra-high purity, localized electrochemical degradation causes rapid battery failure. The data projects a severe market divergence. By 2030, global demand for battery-grade nickel sulfate will reach 1,200 kilotons of nickel equivalent. Operational refining capacity is modeled to reach only 920 kilotons. This creates a structural deficit of 280 kilotons starting in late 2025. Diversifying raw mineral extraction does not solve the supply chain bottleneck. The critical crystallization step remains heavily centralized. China directly controls 76% of global nickel sulfate crystallization capacity. This dominance is sustained by highly integrated chemical supply chains and lower environmental compliance costs. The remaining capacity offers little geopolitical insulation for Western markets. Indonesia represents 11.5% of global capacity, but these facilities are primarily Chinese-backed joint ventures. North America and Europe combined control less than 5% of global refining capacity. Western gigafactories remain structurally dependent on East Asian chemical processing. Crystallization bottleneck is governed by severe chemical and environmental realities. Producing 1 ton of nickel equivalent in battery-grade sulfate requires massive chemical reagent inputs. The process consumes 1,400 kilograms of sodium hydroxide and 1,750 kilograms of sulfuric acid. This intensive chemical reaction yields a highly problematic byproduct. Every ton of refined nickel generates nearly 2.5 tons of sodium sulfate waste. Disposing of this highly saline waste stream is nearly impossible under strict Western environmental regulations. This regulatory friction explains why crystallization capacity remains concentrated in regions with lower compliance costs. To achieve battery-grade purity, producers must also run complex multi-stage solvent extractions, inflating capital costs by 35%. This dynamic mirrors the late 19th century transition to the Hall-Héroult process for aluminum. The primary constraint then shifted rapidly from raw bauxite mining to the chemical purification of alumina. Today, the electric vehicle transition is similarly tethered to a specialized chemical refining bottleneck. Until Western nations reconcile environmental regulations with chemical processing realities, the battery supply chain cannot be localized.